Okay, now we're going to take a look at Marie's register transfer notation, and I do have the notes open over here, so let's go ahead and take a look at the notes. So each instruction in Marie's assembly language can be broken down into smaller steps. We've been building our way up from zeros and ones and gates and decoders and multiplexers and registers and flip-flops. You put a bunch of flip-flops together, you got a register. So we have these registers in the CPU, and we also have main memory. This is usually considered separate from the CPU. It kind of looks like it's all one thing here, but just kind of imagine there's a line right here separating this. Memory would be its own set of chips, and the CPU is on a single chip itself. So there would have to be some wires called a bus connecting the CPU to main memory. And the way that we access main memory is we put an address in here, and the address goes through a decoder. And so let's say that our memory we had 8 bytes of memory. We would put a 3-bit number in here from 0 to 7. It would light up one of 8 lines here that would be connected to the appropriate memory location, and that is the memory location then that would get gated out onto the bus here. So in order to understand how this works, all we really need to know is that a register is a bunch of flip-flops side by side, okay, a bunch of zeros and ones. And we can connect those, each one of those, to an output bus here, okay? And this bus, it says, is a 16-bit bus. A bus is just a bunch of wires that connect one memory location to another. And so we can, I'm going to say zap, we can enable a line here, a bit somewhere, that says, send this data out onto the bus, okay? And let's say that I want to take what's in the program counter, and I want to get it into the memory address register. Well, the way these arrows are set up, it indicates that we're going to gate this out onto the bus, and basically everything else will be shut off. We can only put one set of zeros and ones out here at a time. So put the PC out here, the data will go all the way around, and then if I want it loaded in the memory address register, if you remember when we were looking at flip-flops, all I need to do is have an enable bit on each one of those bits in the memory address register, and I zap that bit, set it to 1, and it will load whatever is sitting out here on the bus into the memory address register. Okay, so basically you zap the output line for the program counter, it gets gated out onto the bus, and it is available to all of these, but in this particular example, we're just going to zap the input line on the memory address register. And so one path around this data bus will allow us to transfer something from one register into another. Okay? So I'm going to select this, and I'm going to open up another program down here. I'm going to open up, if I can find it, I'm opening up my Paint program, paint.net, and I am going to paste in, apparently I didn't copy it, let's go back over here, and I'm going to copy this image. I'm going to paste it in. I'm going to crop it, okay, and then I'm going to draw on it. So I'm going to take my pen here, I'm going to make my pen, a little bit bigger, and I'm going to make it red so we can see what I'm doing. Okay, and now I'm going to flip back over to my Word document, and we're going to take a look. So what we want to do is we want to figure out how every instruction gets executed at the lowest level, down at the register level on our computer. And obviously, when a program gets executed, first we go get the first instruction, we pull it into the CPU, we figure out what it is, we execute it, then we go get the second instruction, we pull it into the CPU, and so on. So there's this cycle that happens when a computer is running called the fetch execute cycle, and before it can execute an instruction, it has to fetch it from memory. And fetching the instruction is the same regardless of whether it's a load or a store or an add or subtract or whatever it happens to be. Fetching it is going to be the same sequence of steps every single time. So the first 4 steps on every single instruction are going to be these 4 right here. This is called a register transfer notation, and all this means is take what's in the program counter and move it to the memory address register, and that will take up 1 clock tick. Then on the next tick of the clock, we're going to take, this notation means M stands for memory, and the square brackets means the memory location that is referenced by the memory address register. So if memory address register says 17, this means go to memory location 17 and copy that into the memory buffer register. This says take the memory buffer register and copy it into the instruction register. And because we're fetching an instruction, that's what we want to do. We want to get it into the instruction register. And then we add 1 onto the program counter to get ready to go to the next instruction. So we always start with 0 at the beginning of a program. PC would be 0. We would copy that into the memory address register, so there's a 0 there. This would take us out to memory location 0 and take whatever we found and load it into the memory buffer register, and that would be the instruction at location 0. Then we take the instruction at location 0, move it into the instruction register. So now we're ready to execute the instruction, and we know that our next instruction is going to come from the next location in memory, so before we do anything else, we add 1 to the program counter. That happens on every single instruction. And if we go back over here, the first step, the program counter always has the address of the next instruction in it. So we're going to take this and we're going to gate it out here, and I'm using a touchpad instead of a mouse, so this is not going to be real slick. And we want to put that into the memory address register. Why do you want to put it there? Because if you want to access something in memory, you have to put the address of what you want to access into the memory address register before you can go get it or before you can write something out to it. So that is our first register transfer instruction. Okay, so now we've got in here is the address of the next instruction that we want to get. Okay, the second step said take what is in memory at the location pointed to by the memory address register and read that in to the memory buffer register. Everything coming in from memory. So we're going to point to a specific memory cell out here, and then we're going to take that and we're going to put it on the bus, and we're going to go all the way around the bus here, and we're going to put it into the memory buffer register. Okay, so now we've pulled something in from memory. That's how we always pull something in. Then we're going to take what's in that memory buffer register, and we're going to copy it to the instruction register. So on the next tick of the clock, it takes a tick of the clock for these signals to settle down. And now we've got that value in here that we want, and then we're going to take that and we're going to copy it, put it on the bus, we're going to copy it to the instruction register. And then the last thing says go to your program counter and add 1 to it, and we actually built a circuit earlier in the semester that was a counter. And so it's easy, if you make the program counter into one of those counter registers that we created, all you got to do is zap it and it goes to the next location. So that happens on every single instruction. 4 ticks of the clock, the same 4 steps. I'm going to clean this up here by backing off. And once you have the instruction is in the instruction register. Okay. Now on these parts, so down here we've got the instructions that we know how to do, and we've got the register transfer instructions for each one of those. So the load instruction is actually these 4, and then once we figure out it's a load, then we do these 3 things. And one thing about my notation here, in the book, she always refers to X for the address part of the instruction register, and I instead I refer to it as the instruction register, and then in square brackets I specify the address. And that would be the low order 12 bits of the instruction register. The instruction register is 16 bits. The first 4 bits are the opcode, and the last 12 bits are the address of the data. So I think this is more clear. But you should know that in the book she uses X instead. So what do you do? How do you execute a load instruction? Okay, well let's flip back over here. let's think about what a load instruction looks like. The first 4 bits are the load, and then the last 12 bits here, so we're going to chop off the first 4 bits. The last 12 bits of the instruction are the memory address. I want to go out to that memory address, and I got to put the address here. I want to read it in, it's going to go here, and I want to load it, so then it's going to go into the accumulator. So that's what needs to happen, and that's 3 steps. So first thing is, if I'm going to load something, I got to go out to memory and get it, and so I have to take my address and I have to put it into my memory address register. Okay, so that's the address of the thing that I want to load. Then that activates one line out here in main memory, and on the next tick of the clock, I take what's at that one location in memory and I read it in, and I go all the way around, and I end up in the memory buffer register. So now I have read something in from memory. And then the last thing I need to do, it's load instruction, and if you're loading, load means take it and put it in the accumulator. So the last instruction is going to take what's here, and it's going to connect it, or copy it into the accumulator. And notice, the accumulator, the memory buffer register, and the ALU are all locally connected. They do not have to go around the bus here to do that, since they have an internal bus here that connects them to each other. Okay, that's the load instruction. Put the address here, read the data in, copy it to the accumulator, 3 ticks of the clock. Okay, now let's flip over, and you can probably figure out what a store instruction is going to do. So these are the steps. This is the only place, I think, where you can do 2 things on the same tick of the clock, and it doesn't necessarily have to be that way either. So we've got an instruction down here, and it says store. Okay, well, what are we going to store? We're going to store what's up here in the accumulator out in memory. And where are we going to store it? We're going to store it at the address that's specified right here. Okay, so if I want to put something out to memory, it's always the same 2 steps. The address it's going to go to goes in here, and the data you want to write out goes here. So the first step then is going to be to take the address part where I want to store it to, gate that out onto the bus, and put that address in the memory address register. Okay, so if I'm doing a store 27, I'll put the number 27 in there. Then the next step is what I'm storing is what's in the accumulator. So I got to take what's in the accumulator, I got to copy it to the memory buffer register, and so now here's my data, and up here is where I want my data to go, the address of where I want it to go. And then the last step says take the data that's in here and gate that out and put it up here and send it out to main memory. Where does it go in main memory? It goes at the address that was specified by my memory address register right here. So that's how a store instruction gets done. Let's undo all of that. And let's flip over, and we've got an add instruction. Okay, let's think about what add does. Let's go back over here. So this instruction says add, and what's going to get added? Well, what's going to get added is what's up here and what's out in some memory location. So the add instruction gives the address of the memory location. So we're going to take the address part of this, and we're going to take it and we're going to gate it out onto the bus, and we're going to put it in the memory address register. Then we are going to read what is there. So this will light up one memory cell. That memory cell on the next tick of the clock will get gated onto the bus, and it always goes into the memory buffer register. So now I have the thing that needs to be added to the accumulator. And the next instruction says add. Notice the memory buffer register is always connected to the ALU, and the accumulator is always connected to the ALU. I wouldn't have drawn it this way. Usually you draw one input on the top of the V, you draw the other input on the top of the other part of the V, and so I would have had this line go up here and connect like that. And the ALU is always written as a funnel, kind of to depict the fact that we got one number here that's going in, we got another number here that's going in, but at the end we get one result out, and that result does go back into the accumulator automatically every time. Okay, so I will send a signal to the ALU. Remember we built that simple ALU in class that did 4 commands. Well, we're going to send an add command to the ALU, and it will add the 2 numbers together. the result will be available instantaneously on this output line, and it will get gated into the accumulator on that tick of the clock. Okay, and so let's undo that. I don't think I need to go back to the Word document. The next instruction is subtract. And so it's in the instruction register here. The opcode says subtract, and the address part gives the address of the number that I want to subtract. And I want to subtract it from what's in the accumulator. So I got to go out and get it from main memory. If I want to get anything from main memory, it is exactly the same thing every time. You take the address from the instruction and you put it into the memory address register. It will light up, one memory cell out here somewhere, and on the next tick of the clock, I want to read what's in that memory cell, so I gate it onto the bus here, and I go all the way around, and I end up putting that in the memory buffer register. And the memory buffer register is always available to the ALU. The accumulator is always available to the ALU, so they're both sitting there just waiting for a command to be sent to the ALU, and the command that gets sent to the ALU is subtract. They get subtracted, and the result is immediately put on this line, and it gets gated into the accumulator, and I now have subtracted something from what's in the accumulator. These are called micro instructions. They are actually smaller instructions than actual assembly language. The opcode 5 is just input, and opcode 6 is output, and that simply involves getting something from the input register and putting it into the accumulator if we're doing input. If we're doing output, we're going to take what's in the accumulator and send it to the output register. Actual input and output is much more complicated than this, but Marie is a very, very simplified version of a CPU, and that's one of the trade-offs they made. They don't show you all the grubby details involved in doing input and output. We just assume that it kind of magically occurs. Okay, and the halt instruction doesn't require any register transfers at all. It just stops the program. The skip conditional, we're not going to worry too much about these, but basically, if the last 12 bits, which would be 3 hex digits, are 800, we will skip over the next instruction. And so 800 means positive. And how do you skip? So we look at the accumulator. If it's greater than 0, then we add 1 to the program count. That's how you skip an instruction. So if we just did instruction 0, and we're going to, the program counter goes to 1 at the end of the fetch part of the cycle. And then if we do this, we will add 1 to the program counter. Now the program counter is 2. And so we will have skipped over instruction at location number 1. And we can skip if the value in the accumulator is negative. We can skip if the value in the accumulator is 0. And skipping or jumping to another location in your program, all that's involved is just stuffing a new address into the program counter. And on the next time around in the fetch part, that program counter will tell us where to go to fetch the instruction from. A jump instruction. Let's flip back over here. So I've got an instruction here. The opcode says jump, and the remainder of it is the address that we want to jump to. So that's the address I want to jump to. And all you got to do a jump is just put the address, get it out onto the bus, and go up here and stick it in the program counter. And when we go to the next fetch cycle, we're going to go to whatever address the program counter is pointing at. So that's how you do a jump. And that takes care of the register transfer notation for all of the instructions that we've looked at so far.